Hey everyone, Charlie here from the Atomic Age, and today we're going to check out some Smarter Every Day. I don't watch Devin's videos too often, but every time I do, really enjoy them. Seen some of his submarine videos and also his ULA Rocket Factory tour video with Tori Bruno. But today we're going to check out his Refueling a Nuclear Reactor video from about 2 weeks ago. It's November 16th right now as I'm recording. And I've never been involved with a reactor refueling, let alone been to a nuclear power plant, so I'm excited to check out this video. I trust Devin, so I know this will be quality, but I hope I'll be able to add some information along the way and explain anything, but we'll see how much actually I have to put in, because Devin is very thorough and a smart dude. But without further ado, let's get into it.
Is that a hot rod?
It is very hot.
That's a very hot rod.
Yes. Back up out of the water would no longer be here. None of us up there.
Really?
Really.
Yeah, super hot. That fuel assembly is going to be super hot. And what they mean by hot is radioactive. With that comes thermally hot, but when you say something nuclear is hot, they mean in a radioactive sense. So yeah, that fuel assembly is putting out an insane amount of radiation. Yeah. Cosmic crap ton. To give a sense of like how much radiation that is in terms of heat, that fuel assembly is putting out a dozen or two kilowatts of heat. And that's, whatever, like I got this space heater right over here. It can put out 1.5 kilowatts. So you're talking about, 10, 15 of these space heaters at full tilt 24/7. So that all that heat comes from radiation. So that's just how much radiation these things are putting out.
And we're going to walk inside an active nuclear power plant, not just like on any normal day. We're going to walk in to a power plant on the day that they're refueling it. They're taking old fuel rods out and putting new fuel rods back in.
He'll probably get into this, but refueling does not happen every day. Not to say that's what he implied, but just to let you all know that refueling takes place every 18 to 24 months. So every year and a half to 2 years. So that's how long you can go between refueling. And even at that point, you're generally only changing out about a third of the fuel in the reactor, while the rest of it gets kind of shuffled around to make sure you're using the fuel evenly. So refueling outages is what they're called. It lasts about a month. Yeah, there's a lot of logistics and planning involved with that. But yeah, every 18 to 24 months is when refueling occurs.
This is the culmination of months of coordination and training and people working behind the scenes to give us this very special look into a very special place.
The amount of training you'd have to do to be able to move around in a nuclear power plant would be a lot, even for me. Every time I switch a company in the nuclear industry, I always have to read all their quality assurance documentation. And that's long story short, that's what the processes you use to prevent errors. Quality control, on the other hand, which you may have heard of, is catching errors after they've already happened. So if you're making a soda can, quality control is looking at it after you've made it, whereas quality assurance is how you design it and control the procurement of the materials and everything to make sure that error that quality control caught never happens. But lots of training, lots of reading. It gets boring, but it's important.
So something's about to happen that we've been wanting to happen forever. We're going to get to go to a nuclear plant.
So visiting a nuclear power plant in this post 9/11 world is a lot more challenging than it used to be. Before 9/11, I remember visiting my local power plant back where I grew up, Calvert Cliffs in Maryland. And you could go onto the nuclear power plant site, not in the plant, mind you, but you could go on the site and they had a museum thing that you could check out. That doesn't exist nowadays. So yeah, it's much harder to get into nuclear power plants for security reasons. Will that ever change? I don't know. It should probably stay that way. Better safe than sorry, right?
And the thing about Philip is he's very moderate.
Very expressive.
This is his angry face. This is also his happy face. All right, this is the third largest nuclear plant in the United States, correct?
I don't know. It's one of the biggest ones. We are the only plant that has all three units under one roof.
Okay. So I'm not certain, but I think this is a boiling water reactor plant. But we'll find out. just because I'm not very familiar with it. I work for Westinghouse, and Westinghouse deals with pressurized water reactors mainly, at least here in the United States.
Neutrons, electrons. So the reactor's actually in there.
I work with neutrons.
This plant, Browns Ferry, was constructed in the 1960s and 1970s and is a huge deal for my local community.
Yeah, so this is a BWR plant. These are BWR containments, which means these are General Electric reactors. These are, yeah, really early BWR containments. Got this odd shape to them. PWR containments are a lot different looking. Will I throw images up on the screen? Maybe. That would be in editing, not right now. But what we can, so you can see with this one under construction on the right here, you can see this lower hemispherical vessel with all the little like pipe cutouts coming out of it. That's for flowing the coolant through it. And then you got this toroidal section here, so that's like this weird little donut looking thing. And yeah, it's been a while since I've looked at BWR containments, like with Fukushima type stuff. It all has to do with how the reactor will contain the steam if all the coolant were to leak out of the reactor. It's very, very different than pressurized water reactor stuff. But let's keep watching.
How's it going? I'm Destin.
Destin, nice to meet you.
Nice to meet you.
Did I call him Devin earlier? I meant to say Destin. I'm sorry, Destin. I guess that's evidence of how infrequently I watch his videos.
I'll need you to step into,
This?
yes, the Gym 5.
Okay. And so what are we doing here?
Radiation protection. I'm the one that issues dosimetry.
Oh, great.
3, 2, be careful stepping out. Clean.
So he made one face into the corner,
Really?
and then he would kill the other one.
It's your dosimeter of legal record.
Okay.
So when this is read, it has dose on it, and you'll have a self-reading dosimeter. It's real time. Well, when you go into the RCA, you'll log into the SRD, but this will be on your person all time.
Okay.
This is stuff that is all like I'm learning along with you guys at the same time. I've never really been in a reactor facility or some area where there's a lot of radiation flying around. I've been in a fuel manufacturing facility, but that's all fresh stuff where there really isn't much radiation at all to speak of. So I'm a desk jockey. I work on a computer. I do computer simulation and analysis. So this is all news to me as well, how the practical side of keeping track of radiation and everything like that. So I'm right along there with you guys. But yeah, so this stuff is just to keep track of radiation in case there's like a leak somewhere or some kind of accident happens. They can quantify how much dose you got, which is, how much radiation you received, and are you in danger? Do you need to be treated, and all this kind of stuff.
And so do you track this for everybody in the entire plant?
Anyone who has to go in the RCA, yes.
Okay.
About 2,000, and during an outage, from there to 4,000.
Wow. That's amazing. You're more intimidating than I expected.
Really?
You are, yes.
Oh, look at that. She's got a big old rifle there. Oh my gosh, I didn't see that.
This is my dosimeter. I should feel a bond with this.
Yes. Do not lose it.
Okay, and so what are the Unit 1, Unit 2, Unit 3? Is that what you call them?
Yes, sir. Yeah, each operating at about 4,000 thermal megawatts, putting out about 1,350 megawatts electric to the grid.
Pretty big reactors.
And we're refueling that. And
Is this a fuel bundle, Bill?
yeah, actually, that is a mock-up of a fuel bundle.
So this is what we're refueling today?
That's right. Yeah, this is the Natrium 11, I believe, is the style on this one.
Okay.
But these are your fuel rods. And actually, you got a good view of the fuel pellets here also.
Sure enough, the exact reactor for Browns Ferry Nuclear Power Plant is in there. Look at that. Those are the fuel bundles.
Yeah, so that fuel bundle, that mock-up they were looking at, did not have the channel. This one shows the channel. BWR, so it's a boiling water reactor. They're a very, they're established now. We know how to operate them, but when they were first envisioned, they were very exotic. I don't want to step on Destin's toes here, but the water boils in the fuel. So like in a pressurized water reactor, which is what I work with, the water never boils. It always stays as a liquid, but in a boiling water reactor, it actually boils. And that makes things very complicated. When they were first thought up, they weren't even sure that it would actually be stable or it could be possible. But yeah, they have these channels so the boiling can happen inside the assembly and kind of be separate from the other assemblies and the water flowing between assemblies, as I understand it. Again, I'm not a BWRs are not my specialty, but I've designed packages to ship BWR fuel, so there you go.
Okay, so how long does it take to come up to, what is 100% in terms of megawatts?
About 1,300 on a good cold river day.
What do you mean by cold river day?
So when the river's cold, it allows us to improve our vacuum in the condenser, which improves our megawatt output.
Really?
Yeah, it's temperature dependent.
Yeah, so this is an old plant. This was built before the EPA passed water regulations regulating how much a body of water can increase its temperature based on something like a power plant. So it looks like Browns Ferry here is cooled solely by the river, whereas newer power plants will have cooling towers to kind of separate that cooling, because you can't, with that EPA Act, Clean Water Act, something in the 70s, you can only increase your body of water by X number of degrees. I think like 2 degrees maybe. Which doesn't sound like a lot, but when you're talking about a whole river, that's a lot of energy to increase the entire river by 2 degrees. And, you know, I might be wrong with the numbers. It's something like that. It's limiting how much heat you can discharge into the river. So, yeah, with them, if the river's hot, this is kind of a different issue. But if the river's hot, it just, from a physics standpoint, you just can't be as efficient as if the water's cold. But yeah, since that act got passed, all the newer reactors needed to have cooling towers installed. So you're not just discharging all that heat into the river. And the cooling towers, that's that typical, this kind of shape thing. I'll probably put an image on the screen. The only thing that's coming out of that is heat in the form of like steam. So there's no combustion happens in nuclear power plants. It's all carbon-free energy source once you're cracking atoms, splitting atoms there. It's just harmless water vapor coming out of those cooling towers. But not only nuclear plants use cooling towers, gas plants, oil plants, they can use cooling towers. So just because you see cooling towers does not mean it's a nuclear power plant. Especially for like Browns Ferry that has no cooling towers. It's only cooled by the river. Some power plants might be on the ocean and cooled by the ocean. Not sure how the temperature increases work over there. Maybe they don't have limits like with the river.
So how long does it take to bring a plant down for an outage, and then versus how long does it take to bring it back up?
So the way we do it for refueling outages, it takes about 12 hours. So we're a BWR, which is boiling water reactor, which means we have contaminated systems throughout the whole station. So there's areas that we can't access at 100% power that we can't access at 40% power. And then we started our outage, so we came down to around 40% power, took heaters out of service, did some inspections, looking for leaks, looking for stuff we would need to fix during the outage.
So you start ramping down,
right?
You take an assessment because you can go more places.
That's right.
And then at that time, you start planning for the outage.
Okay, so we might get to it later in the video, probably not, because Destin said we're not going to look at BWR versus PWR. So one of the big main differences between a boiling water reactor and a pressurized water reactor is that a pressurized water reactor has to first use what's called a heat exchanger or a steam generator. You have to transfer, so let me back up. Nuclear power plants, all power plants that generate heat to generate electricity have loops of coolant until you get to electricity generation. So with a pressurized water reactor, you have your reactor. This is in what we call the primary loop. The reactor here heats up the water. It doesn't boil it, heats it up. And then that goes to a steam generator, which then transfers heat to a second loop. And it does that by turning the water in the second loop into steam, which then goes to a turbine, spins a turbine, generates electricity. And then the third loop removes any leftover heat from that second loop, because you want to get that loop as cold as possible so you can put as much energy into it when it goes back to the steam generator. Boiling water reactor simplifies this a little bit. It combines the primary and secondary loop. So the water that gets heated and turned into steam in the reactor, in the boiling water reactor, then goes straight to the turbine. There's no steam generator. So removing that whole loop gives you increased efficiency. Anytime you have to transfer the heat, you lose efficiency. So on a everything else equal basis, that makes the BWR more efficient. The downside with the BWR is that radioactivity goes through the turbine. Some amount of radioactivity goes to the turbine, activated coolant and such. So that's what he's referencing here with you have to wait for, you have to lower the power and wait for stuff to kind of cool off that can become more accessible. So that's, that'll be different for a pressurized water reactor in terms of areas that you can access and such.
So boiling water reactor means it's designed to have boiling inside the reactor vessel.
Okay.
Pressurized water reactors don't have mass boiling in their reactors. They have nucleate boiling, which means tiny little bubbles form on the surface of the fuel and then immediately collapse. We essentially are at saturation conditions inside the vessel.
So when he says like saturation, that's a thermodynamics thing. That's the saturation of steam. And this, I'd have to kind of refresh myself on this. There's like superheated steam and there's saturated steam. Like coal plants and oil plants get hot enough to use superheated steam. So would like generation 4 reactors that are like triso pebble bed or anything without water in it. Water reactors have to use saturated steam that just can't get hot enough for superheated steam. Oh God. And none of my classmates liked thermodynamics. I was the only one who liked it, so I was the weirdo. What does the saturated mean? Yeah, I'd have to look back up to figure out what the saturated means. Maybe I'll put it in editing, but so that's a thermodynamics engineering term he's talking about there.
So these are literally the steam tables.
Yeah. Oh boy, steam tables. You got to consult these things when you're doing thermodynamics work. At least, when you're in school and learning how to look up these things, I'm sure if you get into the professional world, the software does it all for you.
Correct. Ultimately, you're creating steam to drive a turbine.
Side note, I did not hear anyone refer to a turbine as a turbine until I entered the nuclear industry, and that's what we generally say is turbine. When in Rome, as they say.
It's making me do more training. What am I doing?
You're doing some form material training. So one of the things with the core, it's open, right? So we want to make sure that there's nothing that could potentially drop off you and fall onto the core. We have methods of retrieval, obviously, and if something happened, we'd be okay.
Nuclear industry training. Oh, it gets tedious, but it's important.
Yeah, we're going to go on the refuel floor bridge. So
what is this? Can we look at this?
Yeah, actually, that's a really good picture right there. So what they're doing is, this is a picture of our core uncovered right here.
So this blue that I'm seeing, is that Cherenkov radiation or is that lighting?
Well, that's probably lighting over there. You'll see some Cherenkov. When we pick up another bundle here, you'll probably see it. But there is a blue glow that'll be around the fuel itself.
So if you're watching this video along with me for the first time, and haven't seen Destin's other stuff where he probably talks about Cherenkov radiation, it's so the spent fuel is highly radioactive, right? So some of the radiation emitted off of it is like what we call beta radiation electrons, and these do not go the speed of light. So like photons, like this light shining on me, this goes the speed of light, but electron radiation does not go the speed of light. However, there's a weird quirk in physics here where the speed of light in water is only about 75% as fast as the speed of light in air. So some of this electron radiation emitted by these radioactive fuel assemblies is going briefly faster than that 75% speed of light value. And the result is that blue glow. So that's where the Cherenkov radiation comes from. It's kind of like a sound barrier. It's kind of like breaking the speed of sound for radiation. And instead of a sound, you get light. You get a blue glow light.
Yeah, they've all got specific places where they're supposed to go. We keep very close track of where everything's at, and there's a lot of, I guess I'll say poisons, especially in the spent fuel pool, where we make sure that we can put the fuel and the fuel stays subcritical at all times.
Yeah, so we mentioned poisons just there. Neutron poisons, these are materials that absorb neutrons. And it keeps, so they can store fuel in that spent fuel pool in close proximity without it, starting its own chain reaction. So you put neutron poisons in there and it soaks up neutrons, and you would have to be able to put fuel assemblies closer together than physically possible for them to start a chain reaction, is a way to think about it. Just soaking up the neutrons there. Trying to think of an analog, but it's hard. Yeah, they just soak up neutrons, neutron poisons. Yeah, there's a common thing.
Philip, you were saying don't use like
non-cotton fabrics.
Synthetic fibers tend to have more static electricity, and the static is what radon gets, it will adhere to it. It'll set off the radiation detectors, and then you can, most of the time, you can just let it sit for a little while and it will decay, and you can get it out. It might be the next day, but
that radon is all naturally occurring. That's
not from the plant.
That's not us.
Oh, wow. Okay. Naturally occurring radon is what they're talking about. This happens in, people are probably pretty aware of this because it's a real world kind of exposure to it, but this comes up in basements if you got like uranium veins in the area or rocky stuff. You can get radon accumulation in your basement. So it's not from the plant, it's from Destin's house, supposedly, that would set off the equipment in the power plant. So like radiation detection equipment has gotten so incredibly sensitive these days. It's kind of nuts. And this is an example of it. Just like radon from someone's house could set off the stuff, and it would have to have to sit and decay, even though it didn't come from the power plant. It's fascinating.
There's a Cherenkov.
Oh yeah, look at that! Wow. Yeah. Okay, nice. That's cool.
So how far above the pool will we be?
See it really well in the hole right there.
Oh yeah, look at all that deep blue down there.
We're about to head to the plant. He's our lead guy for valves.
Sitting in these going, we've only got one on right now. I'm like,
oh my god, this is busy. There's lots of people.
Now when you get up there, make sure you let them know your set points for your RWP is 5 millirem dose alarm and 40 millirem per hour dose rate alarm. That's fairly low to be going on the refuel floor.
All right, let's take a chance to look at, let's quantify some of these dose rates here. All right, so what we got here is my handy dandy radiation dose rate chart. So he mentioned two things there. He mentioned a total dose of 5 millirem and then a max dose rate of 40 millirem per hour. So dose rate is like speed in a car. How fast is your car going? And then dose is distance. How far have you gone? If you're going faster, your distance goes up quicker, et cetera, et cetera. If your dose rate is higher, your dose goes up quicker. Yeah. You got it. Okay, so our 5 millirem limit is on this chart. So rem is a American unit, for lack of a better word, and then sievert is the international unit. So 5 millirem is 0.05 millisievert is 50 microsievert. So right here on our chart, our 50 microsievert is dose from spending 1 hour on the ground at Chernobyl in 2010. Okay, so interesting. But overall, it's not a huge amount. You can see here a chest x-ray is double that. And then a mammogram is almost 10 times that amount there. And that's about the yearly dose someone gets from food. And then if we come over here to whatisnuclear.com, they have a low dose radiation effect estimator, which I love a lot. So what this does is you can put in a dose rate and it will tell you how long you have to be exposed to that dose rate to increase your lifetime risk of cancer by 1%. And so that would be, for example, from 42% to 43% lifetime risk of cancer. So if we set this up for 40 millirem per hour, you'd have to be in that environment for 10.4 days to increase your lifetime risk of cancer by 1%. That's obviously pretty extreme, but it gives you a sense of, he did say they're pretty low set points for being inside the reactor, and we can see that here. We can quantify that. It is pretty low. So what that means is that, there could be places in the reactor hall that will get a higher dose than 40 millirem per hour. But again, you'd have to be in there for 10.5 days to increase your lifetime risk of cancer by 1%. And again, 1% is a small amount. Not to say that's good or bad, just trying to give you a sense of what kind of exposures we're dealing with here. But overall, these are very low.
You are granted access to the RCA.
That's pretty big.
Cool.
Deal. No, I really didn't think Bill would pull this off.
Let's not give me all the credit, because if this goes awry, I don't want to be the one that goes down, man. You're going to put your dad on here. Philip will go in last. Just make sure you're all good. You get the green light, and we'll go in.
It's like going on the metro, man.
Okay.
Piece of cake.
Now you got your...
So we're in the RCA now.
We are actively in the RCA. That's correct.
It's very clean.
It is.
I am right here with you guys. I'm right here looking around and seeing all I see. I know the theoretical level what's supposed to be in a power plant, but the practical side is this is all a bunch of news to me. Yeah, there's a lot going on, dude. nuclear power is so complicated. It's arguably one of the most complicated endeavors that humanity undergoes, because, you know, at my company, Westinghouse alone, we have nuclear engineers, we have mechanical engineers, we have civil engineers, we have chemical engineers, sure, a bunch of other engineers, computer engineers, electrical engineers. Like, it's a huge endeavor. There's all this stuff going on. Yeah, it's nuts.
Okay, so what I'm about to take you into is the secondary containment area.
Do we have to badge in to go?
Yeah, we're gonna have to badge in, so I'm first in.
And before we go any farther, when you see the floor drains, don't step on those. They're a lot of times contaminated.
Okay. So be looking for floor drains.
There's so much to keep in track, keep in mind and everything. So, man, it's a lot. So we saw that floor drain back there. That yellow and magenta color indicates, yeah, you know, radiation present, radioactivity.
I'm getting no dose.
Not unexpected, no.
That's how we used to control the speed of the recirc pumps before we had static control. So we've moved over to the recirc drives, but these are some big old motor generators.
It's easier just to leave them there.
Yep.
Yeah, so in BWR space, you have recirculation pumps. And this is a way of how you like control the reaction. It's very different than how PWRs work, which is pretty much all, you know, kind of control rods. But in BWRs, since like the water boils, wherever water is boiling, aka steam, your reaction is not very strong there, if at all, really. But where the water is solid, your reactor is stronger. So with these recirculation pumps, you can kind of like, as I understand it, you know, I'm not up to speed on my BWR operation as much, but as I understand it, like increasing the recirculation pump, increasing how much water is flowing through will, you know, bring the power up, and then slowing the recirculation pumps will bring the power down. I hope I'm getting that right. If not, I'll annotate it in post. But yeah, the point is to use these recirculation pumps to kind of control the BWR, and it's just very different from PWR space. And you know, on paper, they're almost very similar reactors, you know, fuel and water and everything, but just very different mechanisms there.
I'm scared to touch anything.
That's good. Stay that way.
Stay that way?
I have no clear plastic. Do you have any clear
I
plastic?
have no clear plastic.
Thank you.
Not sure what the clear plastic's about. And that's all right. There says don't bring clear plastic. It must be, it's got to be a certain type of plastic that somehow is not good for some reason. I could sit here and think about it forever, but maybe they'll mention it at some point.
Always be nice to people on the elevator. They might be your RP later.
Now I've got to ask you what your RWP is.
My RWP is
Start stuttering now.
121.
The dose alarm is 60 millirem. The dose rate alarm is 250 millirem per hour.
All right, this is what our...
Okay, so his limits there have gone up a good bit. Let's check them out again. Not to say they're anything crazy, mind you. Okay, so his limit before was 5 millirem, which is 50 microsievert? I believe so. Now his limit is 60 millirem, which is 600 microsievert. So we're up here between the mammogram and U.S. government yearly limit on artificial radiation exposure to a member of the public. So he's 60% of that value. But if we come down here, we can see maximum yearly dose permitted for U.S. radiation workers, which is nearly 100 times larger than his current limit. So the guys at that plant can get a much higher limit than a member of the public can, which is, you know, still low in the scheme of things. And if we come over to the low dose radiation effect estimator from whatisnuclear.com, his previous limit was, I believe, 40 millirem per hour. Now it's 250 millirem per hour. And so with the 40 millirem per hour, it was you could stay in that radiation field and increase your lifetime risk of cancer by 1% in 10.4 days. But now it's down to 1.7 days. And this is with a no threshold dose estimation. There's been some like controversy in the news lately, including with the recent nuclear executive orders here in the United States about what is it? It's right there. Linear no threshold hypothesis. Yeah. So that's basically saying like any amount of radiation that you receive is not good. And it kind of, I think it adds it on top of to like whatever you get naturally. At some point that'd probably be an interesting video to do. But you can see also over here, this is like 3,000, almost 4,000 times background radiation. This dose rate limit. So it's not nothing, but it's not a lot either. This previous limit of the 40 milliroom per hour is 600 times background radiation, but it's worth noting that background is still like a tiny amount of radiation. That doesn't mean anything in itself. And basically what this means is like if he reaches any of those thresholds, you know, the 600 millirem or the 250 millirem per hour, he's done. He has to get out of the plant. Oh, we got a lot more information here. RWP limits 450 millirem dose rate alarm at 800 millirem per hour. So that's what the workers at the plant can get. They can get all the way up to that amount. And then we have some expected radiological conditions here. You can go up to 800 millirem per hour. Yeah, that's that peak there. Contact dose rate 1400 millirem per hour. It's a good chunk. Contamination level. Okay, so this is 1,000 disintegrations per minute per 100 centimeters squared. So it's basically a way of quantifying how much stuff has gotten onto you. 10 millirad per hour per 100 centimeters squared. I'm not sure what DAC is. Something I'm not too familiar with. It's not really what I work in, but yeah, this is cool to see. So if we come back to this chart, so Destin's limit was 60, right? So that's 600 microsieverts. The 450 was the for the workers, so that would be like down here for this one event, which is just above, which is right around here. About half a CT scan is what they're allowed to get from this one evolution. Yeah, that's the word I'm looking for, from this evolution. And then their dose rate limit was 850 millirem per hour. And yeah, if you stand in that 850 millirem per hour field, you can increase your lifetime risk of cancer by 1% in just 12 hours. So that's getting a bit more up there. That's a pretty good chunk. For nuclear packages, the dose rate limit at 1 meter after an accident, the maximum allowable is 1,000 millirem per hour. So it's a good chunk, but I mean, you have to be there still for a long time to get some effect from it. And even if they are there for an hour, that's that 8,500, microsieverts. It's still less than a CT scan. So, context. And it's, what is it? It's just under a fifth for the maximum dose they're allowed. 1/6. So cool to see the numbers. I'm trying to do this just to try and give you some semblance of like what to expect from these numbers, because these are all like very low numbers on the whole, but it's like, how low are they? There's different levels of low, but the point is like no one's getting radiation sickness from any of these levels, even if they reach their maximums. Those plant workers not getting anywhere near that. For that, we're talking like, oh gosh, what, another 100 times the dose, so a big chunk more.
So dose rates up there are about 1 to 2 millirem an hour.
Okay.
So that's where we come to our dose rate alarm.
Pretty low.
Dose rate alarm is set.
So the dress out is going to be a full dress out with the single dress out with the hood on the bridge, and that's to protect you because you're going to go into a contaminated area. Contamination levels in the area on the bridge is less than 1,000 dpm per centimeter squared, up to 2,000 dpm per 100 centimeter squared. So the low level.
Okay, so I don't know if I really explained that earlier when I mentioned it. So the DPM is disintegrations per minute. It's just a way of saying how much radioactivity you have. You can convert that to curies, if that means anything to you, or becquerel. You can also convert that to becquerel by multiplying by 60 to go from per minute to per second, or divided by 60, excuse me. And then it's just per 100 centimeter squared, just some chunk of area. So like how much stuff is on a 100 centimeter square chunk that's decaying per second. So, and they're saying it's less than 100 or 200 decays per minute per 100 centimeters squared, which is pretty low. I mean, when you're talking about the amount of disintegrations per minute in that reactor is going to be on the order of trillions. So it's a lot. It's really low, those numbers.
All right, so this is our refuel floor. You got 3 units up here. You can see.
This is cool. But it's crazy that all 3 units are in one building. That's BWR stuff. BWR stuff, man. PWR is to get 1 reactor, 1 containment building. The building here is not the primary containment. So that the reinforced structure that's going to contain the leakage of the BWR is that much smaller thing we saw earlier in the construction photograph. In a PWR, it's the entire building. So like the roof and walls we're seeing here are not really like a pressure boundary like that, compared to a PWR containment building, which is, like a foot or 2 of steel reinforced concrete. Just very different operating parameters. But this is also a very early old BWR. Newer ones have different containment buildings. So yeah, that's why this is all very different than like what I'm used to seeing.
We're currently in refueling operations on Unit 2 right now. They're right over the fuel pool, and they're moving either blade guides or fuel.
So like, again, and as they mentioned earlier, just to point out, this reactor, the Unit 2 right here that's being refueled, the other 2 reactors are currently running at almost full, like one's at full power and one's at like 91% power. So they got like biological shields and lids and everything kind of on it, but that's just crazy to me. That would be crazy to be there and be like, those reactors are running full tilt, basically.
We have 764 bundles in the core, right?
Wow, that's a lot.
Get about 300.
Pressurized water reactor might have like just a few hundred, not 700. BWR bundles are a lot smaller than pressurized water reactor bundles. It's all just the nuclear physics and thermal concerns dictate all this kind of stuff. But I think earlier they mentioned a BWR bundle that's 11 by 11. So 11 rods by 11 rods in one bundle. A PWR bundle is more like 17 by 17, just to give you a sense of the size differences.
You got 4 material individuals out there that are tracked.
Oh, I didn't even notice that earlier. Look at this huge round thing. That's the dome. That is the dome for the reactor, and all those little pegs on the side here, these are all bolts. Wow, that's the dome. God, that thing is big. Hope I'm getting that right. I'm pretty sure I am. That's the dome for the reactor there. Goodness gracious. It's huge.
That's what she said. I'm seeing some people right at the edge of the reactor.
Yeah, those guys are actually part of our in-vessel inspection team. And what they do is they go and they have cameras that they put in the core, look at our nozzles, look at our welds, look at our all that stuff to make sure that there's no wear, essentially, and that the life of the core is maintained.
So I don't think I've really talked about it on the channel yet, but historically on this channel, I've been the nuclear transport guy, so transporting material, but I actually work on reactor vessels now a little bit, doing the analysis for that. So what he was just mentioning, like inspecting the nozzles and the welds. So what I do now is part of what I do now is we analyze the fuel that's in the core and figure out how much radiation is going to be emitted and whatnot, and then figure out how much radiation will be put into the welds and the steel of the pressure vessel and how that's going to affect neutron embrittlement over time, because, hitting the reactor vessel with all this radiation does make it brittle eventually over time, so you want to keep track of that. So that's part of like what I do now too as well, is doing the analysis to check that kind of stuff. So for PWRs, mind you, not for BWRs, but the process would be largely the same, just different way how you model it. But yeah, so they're inspecting that kind of stuff to check on that, so that's cool.
And what is happening now? So he's above the reactor itself.
Yeah, it looks like he's going down to get a fuel bundle at this point in time in the core.
This is awesome, dude. This is cool.
He probably has one latched on. He's coming right now through the cattle chute.
Oh, he can go straight through.
We're moving fuel to the spent fuel
You
pool.
call that the cattle chute?
So they'll get over the location that they want to go either in the core or
see
the
that thing
spent fuel
swinging.
pool.
Should have said, hey, Austin. Did you say Austin?
Destin.
Destin, I'm so sorry. You should have said, 3 years ago, I went to transition into operations, which is a 2-year training program. And I've been a senior nuclear.
But this one's operating, right?
100%.
It literally is 100%.
Literally, 100%. A nuclear reactor loves being at 100% and just hot, fast, and normal all the way. When you are riding this bridge and you're looking down into the vessel, it's really, really neat. It's people are like, oh, there's a nuclear power plant? Where? I'm like, oh, southwest of Athens. Do you like having electricity? 2 million homes. Like, I roll up into some place and they're like, what do you do? I'm like, I'm a senior nuclear reactor operator. You're welcome for the lights. I just corrected you on how to use a ladder. Did you think that?
She did, yeah.
Did you think that you were going to get? He takes it as a piece of thing of I should have looked out for someone like that.
So it's culture.
It is.
Safety culture.
One of the great things about nuclear power is being able to raise concerns without the fear of retribution, and us knowing that we live here. This is our home. We had to take care of it.
Tell me more about that, being able to raise concerns without...
It's called SCIWI. It's the Safety Conscious Work Environment. It's something that the nuclear power NRC mandates that we have. If we had any concern, we can always bring it up. And if you don't feel that anyone is acknowledging your concern, you go to the next level. If you have to do it anonymous, if you had to go straight to the NRC, you can. But no one is going to turn you away on a safety concern.
That's awesome.
It's probably not even worth mentioning, but some of the complete D-bag commenters on some of the Chernobyl series like to say the safety culture thing doesn't exist or matter. And it's like, well, I can tell you've never worked in the nuclear industry, because I point that out as something that didn't exist in Chernobyl, and it really didn't. But it exists here in the United States and probably exists in Russia. Well, not probably. I mean, obviously it exists in Russia today. There haven't been any accidents since Chernobyl. It's something that is taken seriously and that does actually matter, because the nuclear industry knows that there is more money to be made from having this super safe environment. You don't want accidents to happen all the time, because even though they are, with the exception of Chernobyl, rather inconsequential or not as bad as people may have thought they could be, the image affects it greatly. I mean, Japan had nuclear shutdown for 10 years after Fukushima, 10, 12 years. So and no one directly died from that accident, but it's just the perception of it. So it's very important to not have accidents for the health of the industry. So it is taken very seriously, and it all matters. Like every calculation I do, every calculational report I write has to be verified by someone else who is not a part of my process to author that calc note or to create those calculations. They are completely independent. They have to agree with what I put in the report, and even after that, the NRC has to review everything we do. So it's taken very seriously, and it does matter, because there hasn't been any significant accident in the U.S. since 3 Mile Island, and a country like France has never had a significant accident.
Your core map, and it's got every fuel bundle location in the core. You can see the crosses; those are where your control rods normally sit at.
How many fuel rods are there?
764 bundles on each core.
764.
That's right.
That is way more than I thought.
Yeah, there's a lot.
Okay, so there's 764 bundles, but each bundle has about 90 or 100 rods. So you're talking about 7,600 fuel rods. I think there's a little confusion there, but it's a lot. Yeah, I mean, these things are kind of small. They're like about 1/3 of an inch in diameter. But yeah, there's a lot of them.
How do I say this?
It's just an XY map, right? So that'd be rod 4732 is what we call it.
4732. And what is the unit?
Just core location.
Oh,
it's an arbitrary unit that we put up of mappage.
If no one understood what arbitrary unit means, it's just counting the positions. So it's the 47th rod from the right, or 47th bundle from the right, and 38th from the top. That's all that is. Except it looks like, actually for the top and down, it looks like they skip 2. For some reason, it goes like 2, 4, 6. Okay, so I can see why they're doing this. It's an odd even thing. So left to right is odd, top to bottom is even. So it says 47. It's not really the 47th. It's, I don't know, like 24th or something like that. So odd even, so you don't get confused as to which is which.
So who is doing that? Like, who's keeping up with what rods are moved when?
So again, he's referring to it incorrectly here. They're moving assemblies that contain fuel rods. The fuel rods do not get taken out of the assemblies in this process. Only the whole assemblies are moved around. And each assembly is like a 10 by 10 or 11 by 11 grid in a boiling water reactor here. So it's around 95, 90, 100 rods, somewhere in that realm. Not every single position in a fuel assembly is filled with a fuel rod. You leave gaps for water and such, but it's around there.
He's getting our work order number.
This is what we were briefed to, right?
Yep.
6250, we'll hit yes and yes.
All right. So that reset my dosimeter.
It did.
I'm assuming it didn't just reset it. It noted the previous value, but now it's a new value for going to a different area. Oh, back over Devon's right shoulder. Is it Devon or Destin? I'm sorry, I think it's Destin. I can't remember. That looks like a spent fuel cask of some kind over there. I imagine they're about to load that. I could be wrong. I could definitely be wrong, but it looks like that.
Man, I wanted to, everything got itchy all of a sudden.
Well, you got a couple more seconds. You can scratch yourself.
Can I scratch?
Yeah. You're not in the C-zone yet.
Oh, great.
Scratch away.
Everything got itchy.
Your dose alarm is
250. Dose alarm is 60. Dose rate alarm is 250.
dose rate alarm is 250.
I always confuse it too. It's okay, but we gotta make sure you get it right.
All right. You are in officially a C-zone.
We're in the C zone, the contaminated zone.
That's right.
God, that drywall head is huge. Yeah, so this is a first generation BWR, or at least a very early generation BWR with the dry well. It's very different from your PWR. PWR cooling, design and containment philosophy. So that is the containment boundary for the reactor. This building they're in is not really. It's basically just a glorified tin shed. It's more than that, but it's not meant to withhold containment pressure like the big PWR domes. That's what this big dome in front of us we're looking at here is. And each one of those things, I believe I said that before, but each one of those is a bolt. Those bolts are huge. They each have a nut on them. Crazy.
Hey, hold the handrail. Yes, sir. What's your name, sir? Yes, sir. Yes, sir. Yes, sir. Yes. Yes, sir. Yes, sir. Yes, sir. Yes, sir.
I don't think I mentioned it before, but there's a lot of sirs in the South.
Honest service technician.
He just talks like it's no big deal. This man disassembles the reactor vessel for us.
So he knows what he's doing.
He knows exactly what he's doing.
So he's humble too.
He is very.
Just nuclear engineer man, that's all I am. Wow, this is cool. Cool.
Thank you. Never taken anybody up here for this particular instance before. I've never seen this happen before.
This is a big deal.
It's a huge deal.
This is awesome, dude.
So right now you're over the spent fuel pool. You can see we have coordinates. If you really look carefully, you'll see on the walls.
Yeah, they got a lot in their spent fuel pool. You can see a bunch of empty positions down there and all the full positions with several blank positions, probably for cooling purposes. So something kind of tangential to what I do. So I make sure when this fuel, before it's put in a reactor, transported in a package to the power plant, does not go critical. Spent fuel pool, we also want to make sure it doesn't go critical. So yeah, spent fuel pool criticality is its whole own realm of analysis as well. And that can get a lot more complicated because then you're talking about fuel has been in the reactor, so fuel has now been used and such, and there's a bunch of plutonium has been made to some extent, so it's like it gets more complicated than what I do.
He's moving the bundle.
When it comes up out of the hose, see it coming up.
Oh my goodness, I can see the Cherenkov.
Oh wow, look at the glow on that man. Look at that.
It'll come up to a safe height, and then they'll take it and put it in the fuel rack.
It's free right now. I can see it's out of the hole.
Oh, it's spinning. Oh, I didn't think about it spinning. How far down is that? Probably about...
Philip, was that a new rod or what was that?
That is an old one.
Only the old one's going to glow because it has all the... It's super radioactive, super activated, irradiated.
You can tell how it's burnt. See the glow around it?
Yes, sir.
See the tops? They're shiny over there? Them's new ones. You can tell the difference because they'll be shiny like...
Oh, look at that. Yeah, wow, those are really shiny. I'm actually... I guess I didn't know what to expect. Those old ones that are everywhere else but the shiny ones are really dark. I guess that's what you get for being in a reactor for so long. Wow.
So that blue glow I'm seeing is the Cherenkov radiation.
That is correct.
I've never been more aware of my camera.
I'm glad.
And not dropping it.
So it depends how new that spent fuel assembly is, or rather how recently it was taken out of the reactor, but I think it'd be putting out like something like 20 kilowatts of heat. Something insane like that. So like, 12 or 15 or so space heaters running on full tilt. It's a lot of juice, dude. And just like never stopping. I mean, it goes down over time, but it's a lot of heat. And really in the spent fuel pool, that's the concern, is really the heat. All this water blocks the radiation. The concern is the heat and managing the heat. So when the fuel assemblies are spaced out, I'm actually curious, is that more of a criticality concern, so trying to avoid a chain reaction, or is that more of a heat concern? Maybe we will learn that.
Philip said most people think the radiation's green, but it's blue.
So the green thing, I believe, comes from a certain chemical that's used in spent fuel reprocessing. So like making nuclear weapons, for example, like concentrating and extracting the fuel from this kind of stuff, this spent fuel kind of stuff. Yeah, it's one of the chemicals of spent fuel reprocessing that has that green color, which is where that kind of comes from. I'm not sure which exactly. I have to look into that. But yeah. Okay, the senior reactor operator from earlier said we might be able to see the reactor head near the dry well head. I can only see the dry well head, not sure where the reactor head is, so can't see it right now. But we should see it soon.
Can you turn around this way, Bill, and just face that way? Right here.
Oh boy, we're coming over the reactor.
Yeah, swap cameras with me.
So right now we're centering up to go through the cattle chute in order to get into the core.
Yeah.
I love that. It's called a cattle chute.
Holy cow.
You are now officially over a reactor vessel and refueling operations.
Oh my goodness.
Wow, look at that.
So that's a nuclear.
I just gotta take this in. I don't want to talk over everyone, but wow. That is crazy. It'd be cool if they could turn all the lights off, just see the glow from the Cherenkov radiation. But yeah, look at that, man. Crazy. We can already see we got some new assemblies in there. Let's keep it playing.
And they're just sitting there.
What did you say earlier? That's like 50 feet down? Crazy, man. I mean, water is great because it's a liquid shield. You just pump it in, block the radiation. You need a lot of it compared to like steel or concrete, but it's liquid. Just pump it in and out. Can't beat that.
Okay, this is footage from inside the pressure vessel, the reactor core is just down below us. This is what the team is actually doing. The hoist is connected to the whole bridge, which can move in X and Y. Now, at the end of the hoist,
oh, now that I saw that guy rotate there, I don't think that fuel assembly is rotating arbitrarily before he was doing that. That's cool. He's like connected to it.
It offers context for the operator so that they know exactly where they are.
Okay, we're seeing these kind of like corroded, cruddy looking fuel assemblies up close. I guess, yeah, that's just the chemistry of and the radiation and heat of just being in that environment. It's a very intense environment, dude, for sure. But I mean, you can see like down by the edges of this handle, that looks like some kind of cruddy buildup, which is interesting. Wouldn't necessarily think that because the water is moving through here at an extreme rate. But yeah, I'm just like talking out my butt at the moment. Let's keep it going.
They can then do any number of things with the bundle. They can use other cameras to inspect it.
Oh yeah, look at the outside of this. Yeah, it's kind of cruddy, almost rusty looking. So this big thing you see around it, that's called a channel, and that is not steel. That's made of zirconium, a zirconium alloy, just like the cladding on the fuel rods. So like so the fuel is uranium dioxide. It's not directly exposed to the water. It's inside this zirconium alloy cladding. Zirconium is used because it's very transparent to neutrons. It doesn't, that is to say, it doesn't interfere with neutrons all that much. And it's also very ductile, so you can bend it. Think like a cooked piece of spaghetti as opposed to a dried piece of spaghetti, trying to bend that. But yeah, it's very rusty, cruddy looking. I don't think rust is the right word, but some of that stuff on the top would be steel. But this main channel thing here, that is a zirconium alloy.
Because these control rods are so long, if they ever remove more than 2 bundles, that control rod could wobble. So to control this wobble, they have these things called blade guides. Anytime there's 2 or more bundles removed from a certain grid, they insert these blade guides to hold the control rod in position.
Okay.
If you look down into the core, you can see these bright, shiny spots.
Okay, so those weren't fuel assemblies, those are blade guides. Yeah, so control blades, as they're called in BWRs, are very different from PWRs. In a PWR, the control rods are actual rods, and they go inside each assembly through little sheaths. You call them water holes. But yeah, in the BWR, that doesn't happen. Yeah, it's these control blades between assemblies, so it's a very different control structure. They're not just used for stopping the reaction; they're also used for controlling the reaction, kind of leveling the reaction. But we're getting a little out of my wheelhouse with that with the BWR, just not as exposed with the BWR world.
You can see one of those cameras here. You see it's got a long arm and it can articulate. They use these cameras to close.
There's got to be some kind of procedure for like making sure those things don't interfere with each other, like the loading and then the camera thing. That's very interesting. I'm surprised they do that at the same time, but then I'm also not, because like was stated earlier, outage time is a crunching time. There's a lot of stuff you want to get done in a short amount of time. You don't want to keep the reactor offline for any longer than you have to, because you're not making power or money. But there's got to be something in terms of like how the fueling and the camera arm can interact together and not actually interact.
Inspect the mechanical integrity of the reactor vessel and any of its components.
Yes, those guys are inspecting like the welds, which is something I now do work on, is analyzing the welds of the pressure vessel and how the radiation is going to affect their integrity over time, because there's a lot of neutrons in a reactor when it's running, and neutrons hitting materials embrittles that material by displacing atoms, so the neutrons can push atoms around inside a steel crystal lattice, and it basically just weakens the material, makes it more brittle over time. So we analyze it to make sure that it's good, and then they're doing the actual visual inspections of that.
I want to scratch my nose so bad.
Don't do it.
I will not.
I sometimes get a mean nose scratch. That would be difficult. Nose itch, rather. Don't. Oh man, that could. Yeah. Oh, you just gotta sit there. Okay, that's making me antsy just thinking about that.
Does orientation matter?
Yes, orientation matters.
Yeah, so when you design for a cycle, you do a cycle analysis, and that's the people at GE, because this is a GE reactor, will do that. Maybe I think some power plants can actually do their own cycle analyses, but usually they'll come back to a GE or a Westinghouse to do the cycle analysis, and it gets very detailed, like specific fuel rods in a fuel assembly, their enrichment and their location with other fuel rods. All that enrichment can be varied to make sure that the power will be pretty level and that the fuel will burn evenly. So the orientation very much does matter in terms of enacting that plan that was enabled to make sure you get as much juice out of the reactor as possible, and it all stays as you want it. You don't want to have to like refuel early, or one assembly gets burnt up and another's still fresh, or even within the fuel bundle, like different, you want the rods to burn evenly and such. This is crazy, dude. Well, that's steel.
Wow. Is that a hot rod?
It is very hot.
That's a very hot rod.
Yes.
Oh yeah, it's glowing like a mother.
Back up out of the water, we'd no longer be here. None of us up there.
Really?
Really.
Okay, they'd all be toast if that water was
So
gone.
the water's protecting us from the neutrons right now.
And the
At
gamma
least
rays.
6.5 feet or below.
So that was Golf 11?
Yep.
It's had to have happened, and I don't know how often it happens, but there has to. I'm sure at some point a fuel assembly has dropped in this situation, not into the hole, but like dropped and like hit another assembly, then like lays down on top of it. Maybe that isn't a common occurrence. Maybe they design it really well to make sure that doesn't happen. But that's something that I'm sure is designed for. I honestly have no idea, but it's something that could happen.
One of the main reasons people fear this technology is they don't understand it.
Oh, yeah.
But everything was starting to make sense to me. And with that, I was starting to run out of things to be afraid of.
Don't want to hit that button.
What is it, the E-Star?
Seems like it's in a slightly precarious location.
Why is it in the pool?
Well, because it sits on top of the reactor.
Oh, that's right.
Because we boil inside
Ooh,
the
look at that.
reactor, and then we...
In there, in the reactor.
Yep.
It boils,
Yep.
and it goes up.
Yep,
When it goes up, it goes into that.
that's right.
And then, is that like a heat exchanger? Like it bumps? I'm noticing. I'm noticing pipes.
No, All they are like cylindrical pipes. There's
So Destin's thinking more PWR-ish, but yeah, this is just I don't want to speak for Bill here. I'll let him explain. But yeah, separating out the water from the steam. You don't want water to go to the turbine. You want steam to go to the turbine. And then yeah, like with the with the earlier thing, like there's a lot of thermodynamics involved as to which kind of steam we want. Saturated steam, because this can't make superheated steam. It's been a while since I took thermo, but let's continue.
There's no
sealing.
It's
just to make it go in a direction.
That's correct.
Okay.
It's a tortuous path for the steam to go through in order to allow the moisture content to drop.
I see. Okay, and so then that hot water gets circulated out, and then that goes to the turbine, right?
Steam.
The steam.
The superheated steam.
Yes.
Okay, so it's superheated steam.
Because the top is steam.
Right. You want as low moisture content as possible. Right?
Where are we, Bill?
We're on the turbine deck right now. And we're
Turbine deck.
Yeah, we're going to show you what the main turbine looks like.
So for some reason in the nuclear industry, turbines are called turbines, just the way it is.
Typically, this is inaccessible when we're operating, right? You couldn't go to any other units. But this is our main turbine.
This is the turbine?
That's correct.
Yeah, so with the BWR one that's operational, you can't go to the turbine because it's connected to the reactor, so the radioactive coolant is going through it. That's different in a PWR reactor where the loops are separate. The heat is exchanged from the reactor loop to the turbine loop, and those are separate things, so you don't have that same issue with PWRs.
So this is what keeps my lights on. 1,800 RPM is a lot for something this massive.
That's right.
Yeah, dude, that thing's
So
moving.
you have to start it because...
So you can kind of see, actually, that's a good view. You can see some of your pole pieces in the generator right there.
Oh, wow.
Wow.
Much bigger than a car drive shaft.
Here you can see there. Oh, it's interfacing right there. Right. Is that the jacking motor you were talking about?
That's the jacking motor, yeah.
Oh, wow.
Ah.
So this motor...
We're typically around 7 mils at worst.
Really?
On any
Wow,
bearing.
7 mils is something that big.
It's large.
That's like 7 thousandths of an inch.
Where do you buy a turbine?
We have in the reactor that we saw earlier, we have neutrons, right? Uranium-235.
The uranium-235 atom was scary, so I put googly eyes on it.
And I always like the phrase nuclear power equals 120 times the fun. Right? That's an equation for us. NP equals 120F. The speed of the machine times the number of the poles is equal to 120 times the frequency.
Not joking.
Right?
All right, everybody, there you go. Destin's video on refueling a nuclear reactor. Now they've got a lot of other videos coming up, like talking about operating the reactor, putting fuel in the fuel assemblies, like kind of optimizing that. And then I saw a picture of him and one of the other guys, I forget his name, on the spent fuel pad. So, and then he's also going to be checking out stuff at Idaho National Laboratory. So there's a lot of stuff here to potentially check out, and that sounds cool because, you know, I've only been to so few places as a nuclear engineer. I've never even been in a power plant. So yeah, this was fun. Cool to see all the inside of this. He had a video on the second channel that goes into much more of the power plant, a bunch of different other things. Definitely want to check that out. That'll be cool. But yeah, thank you guys for watching. Let me know if you like this, you want to see more, and I'll see you guys next time.